Okay, so let's begin. Let me just start with an introduction. Welcome everyone to today's Fluid Dynamics seminar. It's a really great pleasure to have with us Professor Jens Eggers from the School of Mathematics at the University of Bristol. Jens has been in the UK for a while. He's, as many of you know, he's incredibly well known. He's a master at analyzing flows with interfaces, finding singular structures, and describing very complicated physics with very elegant solutions. And it's really very exciting to hear his results, recent results on the theory of bubble tips in strong viscous flows. So Jens, over to you.
Yeah, thanks very much, Demetrios, for the kind introduction. Indeed, right from the beginning, when I became interested in dynamical pinch-off singularities driven by surface tension, I was also interested in steady solutions to viscous flows, with the related question of how effective is a viscous flow in deforming a free surface into a very sharp and potentially singular structure. So this is the general question I'm asking here. And it's motivated by a lot of concrete physical problems, starting with G.I. Tyler, who in 1934 published a study on how drops and bubbles are deformed by various flows, for example, shear flows or hyperbolic stagnation point flows. And Taylor noticed that when the flow is sufficiently strong and the viscosity of the inner liquid is small, drops get deformed into very, very sharp nearly cone-shaped ends with tips, which are so small and that you can no longer measure them by optical means. Another example is this here. This is a bubble rising in a viscous fluid. Just do the home experiment of turning a shampoo bottle and upside down and watch a bubble rise. And then in the rear of the bubble, you again see this very sharp, nearly axisymmetric tip. And third, very well-known experiment, which we also performed here in Bristol, is known as selective withdrawal. So in selective withdrawal, you have a container half filled with a viscous liquid with air above it. And the liquid is draining through a hole in the bottom of the container. And the resulting flow deforms the interface between liquid and air once more into this very sharp tip. And we did now almost 20 years ago a series of very precise measurements, which will feature a little later in this talk. Let me just also mention that axisymmetric cone-like structures arise in many different situations. Here is an example of an electric jet where an external electric field deforms the liquid into a cone-like structure out of which a very thin jet emerges. And I will turn to this question of secondary jet-like structure at the very end of my talk. Okay. I've stressed that the structures I'm looking at here are 3D axisymmetric structures. So it's important to differentiate the singular structure I'm investigating from another nearly 2D structure described originally in a brilliant paper by Jeong and Moffatt. And these are two-dimensional cusps. So here is an experimental example. Once more, you have the interface between a viscous fluid and air, and the flow is driven at some speed v by a cylindrical roller. And the viscous drag by this roller deforms the interface in this sharp cusp. Of course, in reality, this is not a 2D structure, but it's nearly 2D. And the fact that it's a 2D structure means that the tip of the cusp here is now a line, and the flow is focused all along this line. And if I make a cut to this setup in the plane of the screen, I get something that's very nearly two-dimensional, and in any case can be described by two-dimensional mathematics. And here's the experiment by Laurenceau, Restagno, and Quéré. So they measured, among others, the neighborhood of the tip of this cusp, and measured the radius of curvature. And as function of the capillary number, which is a non-dimensional measure of the characteristic speed of this roller V, and they found that the radius of curvature decreases exponentially in the capillary number, that is, in the strength of the flow. And this is exactly what was predicted by Jeong and Moffatt. So Jeong and Moffatt proceeded by setting an exactly solvable two-dimensional problem, which consists of a fluid of infinite extent, horizontal extent, driven by an ideal vortex dipole below the surface. And using complex methods, that is, using the two-dimensional structure, they were able to find an exact solution to this problem, which they then analyzed. And so this is the result. They found that the neighborhood of the tip here is in the form of a similarity solution. And here is a close-up of what you would see near the tip, where the characteristic scale of the similarity solution is this radius of curvature R, which, as I've said, has this exponential dependence of the capillary number, which is, as I said, the characteristic speed divided by a characteristic capillary velocity, gamma surface tension divided by viscosity. And not only that, if you bring the solution near the tip of the cusp in similarity form, you see it has this similarity form with a universal shape of the interface near the tip that only contains this one free parameter A here, which depends on the details of the outer flow. So this is the situation with these two-dimensional solutions. Curiously, it's all based on these exact solutions. People subsequently have found other solutions, but no one has ever done a systematic asymptotic analysis of the viscous flow equations to obtain this same answer, which is, I think, an interesting project to be done. But I focused on the three-dimensional axisymmetric problem. And apart from its practical relevance in experiments, there's a fundamental question of whether in this situation, the tip of the bubble you've seen really has zero radius of curvature, or does it remain smooth? And that's a non-trivial question, because in any case, you would expect the structure in this three-dimensional case to be smaller, the problem to be more singular than the two-dimensional case, because in 2 dimensions, the focusing of the outer flow is along a line, whereas in this 3-dimensional case, all the flow lines focus towards a single point. So in some sense, this represents a worst case scenario for smoothness. And if it turns out to be smooth in this case, then you can pretty safely say that all stationary flows with surface tension will remain smooth. And in case they're smooth, then in case there's a finite curvature, how does this curvature grow with the capillary number, which is this non-dimensional measure of the flow strength? So this is the scientific question I'm asking. Just to give you a feel as to what has been done on this problem before, Taylor himself, some 30 years later, developed a theory for the shape of bubbles in external flow. And this is based on what's known as slender body theory. In slender body theory, you suppose a distribution of singularities, in this case, typically sources and Stokes slit singularities along the axis. And then in a perturbative sense, you adjust the strength, the distribution of these singularities on the axis so as to satisfy all the boundary conditions. And this can be done in a perturbative way, in a perturbation theory, in the slenderness of the drop, essentially. And Taylor was able to set and solve the leading order equation, which would predict conical ends, that is infinite curvature at the tip. And so to work out what actually happens at the tip, Buckmaster, some years later, took this up again and formulated the theory to the next order. And he ended up with essentially an inconclusive answer, in that he was able to calculate the additional terms, but he noted that the expansion he was using broke down near the tip of the bubble, which is not surprising, because the bubble may be slender in a strong flow, but it's certainly not slender near the end, where it has to be rounded. And that's a perennial problem for slender body theory, what to do near the end of these bodies, wherever you apply it. And there are many situations where this problem arises. So once more, the question here that's not answered by slender body theory is, what is the tip curvature actually? Is it even finite or infinite? Even that was not known. So there's one more piece of information as to conical tips. One thing actually tried by G.I. Taylor himself was whether the full Stokes equations, the full viscous flow equations, would allow for a similarity solution in the shape of a perfect cone, which would then have a true tip that is infinite curvature at the end. And he found, G.I. Taylor found, and Buckmaster later confirmed, that there is no similarity solution of this type. And so to give away the answer to everything I'm going to say subsequently, I'm going to show you what actually happens near the tip based on some numerical solution to the problem, which I did now more than 10 years ago. And so here you have a sequence of panels that shows the interface close to the tip. So this is all relative to the tip. The first panel here shows the interface on a scale of order 1. And you see that the interface from the numerics agrees rather well with the dashed line, where the dashed line is the result of Taylor's leading order theory. But as you zoom in to the tip, so for each panel, the magnification factor is increased by a factor of 100. So this is now on a scale of 10 to the minus 2. This is 10 to the minus 4, 6, and 8, and so on and so forth. And so what you see is that for each panel, the more you zoom into the tip, the slope of the interface increases. So indeed, the solution is not a cone, but a near cone whose slope increases very, very slowly if you zoom in. So the main message is that the slope of the interface is resolution dependent. If you perform an experiment and zoom in with a microscope into the tip, you will see a different slope from what you would observe with a moderate magnification. And so my subsequent theoretical analysis is based on this idea that you have a near cone whose slope changes very slowly. And as I said, the dashed line is Taylor's slender body theory. Okay. So the first idea is that just as Jeong and Moffatt have done, we want to describe the neighborhood of this tip with a similarity solution, and we guess that just as Jeong and Moffatt, the characteristic scale of the similarity solution is the tip curvature, or the inverse tip curvature. And this works rather well, as we've already described in this 2009 paper, where we present numerical solutions to, first of all, a bubble in an extensional flow, and then also the same thing for the selective withdrawal geometry, which is a very different geometry. I don't even know which is which, but the message is that regardless of the global geometry of the flow, if you rescale in the similarity way, that is, if you plot things as a function of the distance from the tip and you represent everything in units of the inverse curvature at the tip, everything collapses towards a universal shape. So that's the first idea. Of course, the question now is, what's the best framework to actually calculate these shapes? And somewhat unusually, I will base my calculation on the so-called boundary integral representation of Stokes's equations. So the boundary integral equations are equations that are usually used for numerical purposes, and indeed I've used them in 2009 to calculate the flow numerically. But here I want to use them as the basis for an analytical calculation based on this idea of a cone of slowly varying slope. And just very briefly on the logic of these boundary integral calculations. So the velocity field is only calculated on the surface of a shape. That's this integral over S. And the velocity on the surface is represented as an external flow. That's the external drive, like a roller. Then comes a contribution from the surface tension. And finally, there comes a sort of correction factor, which comes from the fact that if the inner and outer fluid have different viscosities, there is a jump in the stress across the interface. And to correct for that, you need this extra factor here, which is particularly bothersome because it turns the whole thing into a true integral equation, because you have to, because the velocity field now is inside the integral here, instead of the velocity being explicitly in terms of this integral over the curvature here. Okay, and according to what I've just said, I'm rewriting this equation in a different form. The first step is that I perform the azimuthal integration. So now V only has components Vz along the axis and Vr in the radial direction, because I integrated out the azimuthal component. So what you see here is essentially a 2 by 2 matrix. And the other important manipulation I've done is, since I expect the solution, the slope, to change very slowly on a logarithmic scale, I transformed into logarithmic variables, L. So L is now the logarithm of zeta, where zeta is the non-dimensional distance from the tip. And this variable R here is a non-dimensional curvature. It's the curvature at the interface made non-dimensional with the length of the drop. And from now on, velocity will always be given in units of gamma over eta, which is this capillary speed. So, which turns the velocity essentially into a capillary number. And there's one more little trick here. Namely, I represent the interface in a slightly different form. Instead of my original similarity solution, h of zeta, I anticipate that this locally, this shape is close to a cone. So I write it as being proportional to zeta times s, where s, think of slope, depends very slowly, namely logarithmically, on the distance from the tip. So this is the framework. And as I said, using this framework, I've turned everything into a problem with two components, Vz and Vr. And I represent this Vj integral with these two components here. And the second integral is this matrix of k values. But of course, this looks harmless, but it's not. It contains the full integral. So in this representation here, any part on the surface is still coupled to any other part of this of the surface, and you can't do anything with it without further simplification. So what is the crucial simplification? And I've got a pictorial representation of what's going on a logarithmic scale here. So in this plot, you see a representation of the tip. So this is the function h of zeta. And I will use the fact that if you go away from the tip, the slope of the interface becomes small. So I will, in the end, expand everything in small slopes. But let me just go back. The even more important observation is that, as you can see, for example, here, if you plot the kernel of any of these integrals as function of the integration variable L2, you see that the kernel is very sharply peaked around the value L1 I'm looking at. So the strategy will be, in the end, to perform a systematic expansion around this peak. A perfect peak, a delta function, would mean that the integral goes away and everything turns into a simple matrix relation. But you can see here that things are not always so simple. So this is another integral here. So this is the kernel of the J integral. And again, you see a sharp peak, but you see that to one side, this peak also has a long tail. And this, as a result of this, we will see that in the case of this integral, the integral actually does not converge as the upper limit goes to infinity. And you have to make special allowance for this divergence here. Okay, so as I've said, I'll anticipate and I'll later confirm that the slope goes like 1 over the square root of L, where L is the logarithmic distance from the tip. And so I plug this into the expression here for the curvature, which to leading order, that's just the radial part of the curvature, just goes like 1 over the slope. So I can plug in this value. And I can also analyze the behavior of the rest of the kernel. This is this red line here. I analyze asymptotically the behavior of the rest of the kernel for large arguments. And this is the result you find. It's this red line here is a power law on a logarithmic scale. And if I put this together, you will see that this integral here, well, this integral you can see goes like S is proportional to the slope. The slope goes like 1 over the square root of L. So of course, at the upper limit, this is a diverging integral as advertised, which is the principal reason why you have this unusual logarithmic behavior in the first instance, because if all the integrals were perfectly convergent, then everything would ultimately turn into a local problem, and then a cone solution with constant slope would be a solution. But we've already seen that that's not the case. So you do expect that something goes wrong, as it were, with these integrals, and that you have divergences. Let's, as another example, look at one of the K integrals, these integrals that come from a mismatch in the stress. So this is now the form of the kernel. You've got this factor of zeta 2, by the way, which comes from the fact that we've transformed to logarithmic variables. And this kernel here is multiplied by the velocity at L2, where L2 is the integration variable. And the intuition is that the main contribution to this integral comes from this peak here, in which case, to leading order, Vz of L2 can be replaced by Vz of L1, because V varies slowly on the scale of this peak. And that's what I've done here. First of all, I've changed the integration variable to the variable relative to the peak position L1. And I've let to leading order the limits of this integral go to infinity, because all the major contribution just comes from this peak here. And so how do I deal with this kernel here? This is still a complicated function of two variables. So I deal with this kernel here by expanding in the slope, using that the slope is small. It turns out that leading contribution to this integral, and I will expand on this a little bit later, comes from a region of size S, size of the slope, which, as we know, is small. So I expand the kernel into a power series in S at constant psi, which is the delta variable on the scale of the peak, and only take the leading order contribution. And so now I get an integral, which is just a number. It's just an integral over psi. And it turns out, again, I'll comment that a little later, that I can do, although this is a horrible integral, I can do it. It's 1/2. So the result of this whole integral here turns out to be the velocity, z component of the velocity over 2. And I can do the same thing for all of the other integrals that appear in this expression. And if I do that, I get a set of equations where this is the z component of the matrix relation I've shown you, and this is the r component. And all these coefficients were calculated in a way very similar to what I've just described. And I have another condition, namely that for a steady flow, the surface of my drop is a streamline of the flow. So now I get a system of 3 equations for 3 unknowns, namely S, Vz, and Vr, and it's a very simple matter to solve this set of equations. And I get asymptotically far away from the tip for large L that the slope, indeed, this comes from the equations, goes like 1 over the square root of L as advertised, where L0 is an integration constant, which I have to determine numerically by matching to the immediate tip region. And so in the first test, this is compared here to the experiments of Sylvain Corrège-Dupont using the selective withdrawal geometry. The solid line is a full numerical simulation of the problem, and the dashed line here is the result of this leading order theory, which, as you can see, works very well. So this is the similarity solution near the tip, and you see that but rescaled in this similarity way. And you see that as the strength of the flow increases, as the curvature goes down, this approaches more and more the theoretical solution. And you see that even better on a logarithmic scale, where here is the curvature. So the curvature increases as you go from the top to the bottom. And you see that as the curvature increases, the experimental profiles more and more match the theoretical prediction. What's even more interesting is to determine the tip curvature itself. So how do I determine the tip curvature? Well, I plug this solution here back into the equations. So this is the Z balance of the equations with the solution S equals 1 over square root of L plugged in. So this is an integral here I can very easily do. And I see that it matches. That is, the L dependence of the right-hand side matches the L dependence of the left-hand side. And I get an expression for the curvature, the tip, as function of the capillary number. And so this, if I solve that for kappa, for the tip curvature, I find that the tip curvature goes like some inverse length scale, which I don't know at that point, times an exponential of the square of the capillary number. So indeed, exactly as suspected, the curvature grows a lot more quickly, namely like the exponential, the square of the capillary number, much more quickly than in the two-dimensional cusp solution of Jeong and Moffatt. And again, this has been compared to the experiments on the selective withdrawal geometry. And once more, the solid line is a numerical simulation, and these round symbols here is the experiment. And the theoretical prediction here for the growth of the tip is this dashed line here. Okay. So why do I want to go on from there? Well, first of all, one problem with this solution is I don't know what this prefactor is. So I don't really know how a length scale associated with the bubble comes into this. And also you notice that the slope here of the dashed line is slightly greater, it looks to me, than what's actually observed. So this is what I want to investigate further. And for this reason, I'm going to pursue the calculation I've just done to the next order, which you need to answer these questions. So the second order calculation, I'm doing it because I want to know what's the amplitude in front of the tip curvature. And I also want to know how does it all fit together? How does my local tip solution actually fit together with the description of the slender body theory proposed by G.I. Taylor? And so this becomes a little painful, but very, very interesting, I find. I'm just going to sketch how you proceed at the next order. So the first thing is I just pursue the expansion in the logarithmic slope to next order. So this is the leading order result, and now comes the next result, and I do that for the z component of the velocity and also for the r component of the velocity, where it will turn out that these coefficients here actually are logarithmically dependent on L. So we have logs of logs. And also, the crucial point was that I have these kernels which are sharply peaked, and I have to do this systematically. So this is a systematic local expansion around these peaks where the integrals are centered. And if I do that for one of the kernels, I get, don't be concerned about this complicated expression. I just want to give you a flavor of what happens. So this is the r component of the integral that represents the contribution from the surface tension. So this here is the leading contribution from the curvature. This is just an expansion of the curvature. Remember, the leading order term was just 1 over the slope, and now you've got some extra terms. Times the kernel, which comes from the boundary integral description. This is the leading term which we considered before. But according to this expansion here, now I also have higher order moments. So this is a 0th order moment in delta. And now from this here, I've also got a 1st order moment in delta. And I also have to take into account that the kernel not only depends on the slope itself, but also on the derivative of the slope. So I just have to be patient and have to take into account all of these contributions. And finally, I also have to take into account that I have to expand the curvature itself here in the same way. That gives me this object here. So it all boils down to evaluating a lot of integrals, which I've called I0, I1, I2, I4. The point is that in all of these integrals, I'm effectively integrating over cones because I'm doing this expansion. I've eliminated the dependence on S2, and effectively I've reduced it to a moment expansion of integrals over a surface at constant slope, which makes them doable. So that's the central idea. And there I'm using the fact that the slope varies slowly, only logarithmically. So how do you do these integrals? I just want to give you the flavor. So this is a typical shape of these. These are the type of integrals I have to do. They depend on S, the slope, and the distance of the integration variable from the reference point. And the problem with these integrals is that they go from, should be minus infinity to plus infinity, of course, that they go from minus infinity to plus infinity. So you need a global description of this integrand here, which you can treat in a rather standard way by having an inner expansion. This is what we did before. This is realizing that the main contribution to the integral comes from an interval of scale s, whereas it's the slope, but there's also an outer part which at higher order contributes. And so to do this integral, you find a global description of your function by matching together the inner and outer solution, and that gives you a systematic expansion in powers of the slope. And this is a flavor of what you get. You get powers of the slope, but you also get logarithms of the slope. And finally, very quickly, then there are these magical numbers which appear here, which are also integrals you have to do. And I just have to very quickly show you how I do these integrals because it's really cute. So this is what you're up against. These integrals you still have to do, which are just numbers, are integrals over algebraic functions of psi and these k and e, where k and e are itself elliptic integrals. So you have to do integrals over elliptic integrals, which are not in Gratstein-Rishik. So you have to think of something else. And the rather amusing trick I use to do these integrals is that there are the kernels I'm talking about that appear in the boundary integral description obey some exact relations, which are basically manifestations of the divergence theorem. So there are some exact relations involving these same integrals. So here's an example of an exact integral I know. And so if I expand, this is true to all orders of S. So if I expand this integral here, I rather get a whole hierarchy of exact identities, all involving these logarithmic integrals. And by using linear combinations of these exact identities, I can actually cook up something which is exactly my integral, and this is what allows me to do the integral. Okay. So if you do this, you turn the crank, you do all systematically to next order, and you once more get equations, flow equations, I call them, involving my variables S, VZ, and VR. So these equations written here are exactly the analog of what I've wrote before. And you can solve them. So this was the leading order solution. And now you've got the next order, which goes like 1 over L to the minus 3 halves. And amusingly, they contain the logarithm of val, that is the log of a log of the distance from the tip, and log squared of val. But they work rather well. So here you could see a comparison of this asymptotic behavior of the similarity solution with full numerical simulations. And this parameter L0, this integration variable, has been fitted using this panel here, and then these results here are the prediction without adjustable parameters of this expansion. You see this expansion works extremely well. But it gets better if we now compare what we've done to what the previous theory, namely the slender body theory, gives. So very briefly, so this is the slender body theory, which was pushed to higher order by Buckmaster. So as I said, you represent the flow, so this is the stream function of the flow, as a distribution of sources with density F and Stokeslets, that is force singularities with density G. And you have a new expansion parameter, which is epsilon, which is essentially the inverse of the capillary number, the flow strength at the tip. And you expand everything in this epsilon. And this is a calculation whose structure was written out by Buckmaster. So I've redone this calculation doing all the integrals. And what you find is that the inner limit of this expansion, now this is an expansion where everything is in units of L, in units of the size of my drop. And the inner expansion of this outer solution has this form here. And the question now is, how to reconcile this form of the solution with the similarity solution of the tip, which I've just found, that is to form a matching. And this matching is indeed possible. I have to compare these two things. So H of zeta is the similarity solution I've presented. That's the similarity solution of the tip. And away from the tip, I have this outer solution by Buckmaster. And these solutions, two solutions, are related by this parameter R, which is this dimensionless curvature of the tip times the length of the drop. So in the previous slide, I've given you the inner limit of the outer solution. And this here is the outer limit of the inner expansion, at the outer limit of the similarity solution I've just calculated. And my calculation was set up precisely to look at the outer limit away from the tip. And so comparing this to the inner limit I've just shown you, the question is, can I choose R such that it matches the outer solution? And that's possible. So if I choose epsilon, which is the capillary number at the tip, to depend on R in this way here, the two solutions turn identical. So they match exactly term for term, and that's non-trivial. The fact that they do depends precisely on some of these exact numbers I get from the calculation. So you better get all these numbers right. And this is the answer to my question, because epsilon is the capillary number for the tip, and I just have to convert that into the tip curvature. So that's the result for the tip curvature to second order. So this is what I found before. That's the tip curvature, which grows exponentially with the capillary number at the tip squared. But now there's a prefactor, which I now know, and it's this here. Okay, so first of all, this is the result I had before. This is the dashed line here. But since, first of all, I have the correct amplitude, so the dotted line is a comparison with the full numerics without adjustable parameters. So the dotted line and the solid line better agree, and they do pretty well. And the reason that it looked like the slope wasn't exactly right is that the prefactor depends very slowly, logarithmically, on the itself on the capillary number. So that makes for a very slow variation of the slope here, which is the reason why at first order it looks as if things don't exactly agree. And so this is really the highlight of the talk, and I better stop here. I just wanted to show you this picture here, which is sort of the next problem that's around. This shows one fluid interface being deformed in a microfluidic setup, and very often you see very similar to what I've described, conical shapes, and out of the tip of this conical shape you get a thin jet, which is a phenomenon known as tip streaming. And now that we have an understanding of these conical structures, the hope is that we can approach the birth of this secondary structure as well. And this is based on these two papers which came out very recently. Thank you very much.
Great, thank you very much, Jens, for a very inspiring talk. Lots of nice details and beautiful solutions. So we can now open the floor to questions. Any questions, please, from the audience? And if not, I can open with one, ask one. I guess when you decide what the form of H is, so you make H to be zeta times S of log zeta.
Yeah.
Is it obvious it should be log zeta and not log zeta, or some other, slowly varying?
Yeah, I mean, it's probably the result shouldn't really depend on it. I mean, one nice feature of the log is that actually tells you it's the natural scale, is that something I've briefly mentioned. If you do this log transformation, you get these additional factors zeta, which look as if the integrand would be not logarithmic, but strongly dependent on zeta. But that's not the case, because if you look at the definition of these kernels here, they actually go like 1 over zeta. So it's precisely this logarithmic transformation which make these expressions here scale invariant. So for that reason, the logarithmic scale actually comes right out of the formulation. Right. But I mean, if you were if you were a masochist, in principle, I mean, of course, if you decide on log, ultimately, if you do the calculation correctly, you should get the same answer. I mean,
right. Yeah. Good. Okay. Thank you.
There was a raised hand somewhere.
Shu Song, you have a question.
Mute myself.
Oh,
I can hear you.
We can't hear you, Shu Song.
Yeah. Okay. Can you hear me now?
Yeah, I can hear you.
Yeah. Very nice. A very nice talk. So you used this integral formulation.
Yeah.
But alternative, you don't have to, right? I'm sure you have your very good reason to do that, but you can stick with differential equations.
Yeah, I mean, originally, it took me a very long time to decide on using the integral formulation. I mean, initially I tried to formulate, similarity solutions to the equations of motion directly, and it's not
Yeah.
impossible that that might also work. But the reason the integral formulation is actually quite nice here is the following. The difficulty with the integral formulation, boundary integral formulation, and why it's only used numerically in most problems is that it's an integral over an unknown surface. So the integral is over the surface of the drop, which yet you don't know.
Yeah.
And so that's terrible because you don't know anything about this, this integral. But what makes it work is the fact that effectively, locally, you expand around the conical shape. And the conical shape, you know. So you can, in the end, using this expansion, reduce everything to integrals over a known shape. And that, in the end, if you're sufficiently patient, allows you to do the integral. So it all hinges on the fact that you've got this very slow variation of the slope. Otherwise, you'd be lost and you wouldn't gain anything from the boundary integral description.
Yeah. Well, I find the techniques, okay, it's very impressive, but I couldn't quite recognize it. You know, whether I can see you can match those. You have in or out solution matching is there, but you also have this kind of stretched coordinates and this multi-scale. But again, they are not those kind of standard techniques. So.
No, they're not. But what I also found helpful is thinking is that, as I've indicated here, you see this one kernel I'm pointing at is actually not P. It has this long tail.
Yeah.
It's actually because of this long tail that the solution has this complicated structure. If all the integrals were convergent, then a local approximation to the cone where everything has a constant slope, you can see immediately that that would be a solution. But it's because of the divergence of this integral that the similarity solution failed, which is, you can see directly by inserting into the Stokes equation. And my original idea was, and it's still not clear that that can't work, but somehow my hope was that I could modify these conical similarity solutions to cook up a true solution to the problem, but that hasn't worked. And the only thing I've got to work is this integral formulation, which works quite nicely if you are patient. And I just did this over the pandemic phase, and I had a lot of time on my hands, and that allowed me to do it essentially.
Okay, thank you.